You're moving right now. Faster than a bullet. Faster than sound. Faster than anything humans have ever built. And you don't feel a thing. The galaxy you're sitting in, yes, you, right there, reading this, is hurtling through space at 2.1 million kilometers per hour. That's 583 kilometers every single second. While you blinked just now, you traveled 1,166 kilometers through the cosmos. But here's what shatters everything you think you know. That's not even the real movement. The universe itself is expanding. Not into something. Not from something. Just expanding. Space itself is stretching, pulling, growing between every point in the cosmos. And the speed of this expansion? It defies every law of physics you've ever heard of. Because galaxies at the edge of the observable universe aren't just moving away from you. They're receding faster than light itself. Impossible, you say? Welcome to the single most terrifying mystery in all of physics. Let me take you back to 1929. A man named Edwin Hubble, yes, that Hubble, the one the telescope is named after, made an observation that would shatter our understanding of reality forever. He was studying distant galaxies, measuring their light, and he noticed something impossible. Every single galaxy he observed was moving away from us. Not some galaxies. Not most galaxies. All of them. Imagine standing in a room where every single person suddenly starts walking away from you. In every direction. At the same time. You'd think you were the problem, right? You'd check if you forgot deodorant. But here's the twist that makes this truly mind-bending. It wasn't about us. Every galaxy was moving away from every other galaxy. If you were standing on any other galaxy in the universe, looking back at us, you'd see the exact same thing, everything moving away from you. The universe isn't expanding into empty space. Space itself is expanding. New space is being created between galaxies every fraction of a second. Right now, as you read this word, and this one, Hubble measured the speed of these galaxies. He found something that would become known as Hubble's law. The further away a galaxy is, the faster it's moving away from us. A galaxy twice as far recedes twice as fast. 3 times as far? 3 times as fast. Sounds simple, right? But wait. Let's do the math. And this is where your brain starts to hurt. Hubble calculated what we now call the Hubble constant. It's the rate of expansion of the universe. Current measurements put it at about 70 kilometers per second per megaparsec. What does that mean in language humans can understand? For every 3.26 million light-years of distance, space expands by 70 kilometers every single second. That might not sound like much. But space is big. Really big. So big that your mind cannot comprehend it. Let's start small. Our nearest major galactic neighbor is Andromeda. It's 2.5 million light-years away. At that distance, you might think it's receding from us at about 54 kilometers per second, right? Wrong. Andromeda is actually moving toward us. At 110 kilometers per second. It will collide with our Milky Way in about 4.5 billion years. But here's the thing, this is local movement. Gravity between our galaxies is stronger than the expansion of space at this distance. Andromeda and the Milky Way are like two people holding hands in a crowd that's spreading apart. The crowd spreads, but we're holding on too tight to separate. But go further. Much further. The Virgo cluster of galaxies sits about 65 million light-years away. At that distance, the expansion of space carries it away from us at roughly 1,400 kilometers per second. That's 5 million kilometers per hour. Fast enough to cross the distance from Earth to the Moon in just 5 minutes. Still with me? Good. Because now it gets terrifying. The Coma cluster. 336 million light-years distant. Receding at 7,000 kilometers per second. That's 2.3% the speed of light. In 1 second, it moves further away than the width of Europe. But that's nothing. That's a gentle breeze compared to what's coming. Go to galaxies 4 billion light-years away. They're receding at 93,000 kilometers per second. That's 31% the speed of light. These galaxies are moving away from you so fast that if they emitted a beam of light in your direction right now, that light would be swept backward by the expansion of space for millions of years before it could even begin to make progress toward you. 6 billion light years? 130,000 kilometers per second. 43% light speed. 10 billion light years? The recession velocity hits 220,000 kilometers per second. That's 73% the speed of light. And here's where Einstein's ghost starts screaming. At around 14 billion light years, near the edge of our observable universe, galaxies are receding from us at speeds exceeding the speed of light. Some calculations put the recession velocity of the most distant observable objects at over 3 times light speed. But wait, you say. Einstein proved nothing can move faster than light. That's the cosmic speed limit. The law that cannot be broken. You're absolutely right. And absolutely wrong. Because those galaxies aren't moving through space faster than light. Space itself is expanding between us and them. And there's no speed limit on the expansion of space itself. Einstein's law says nothing can move through space faster than light. But space itself? Space can do whatever the hell it wants. Imagine you're an ant walking on a rubber band. You can only walk at ant speed, let's say 1 centimeter per second. That's your speed limit. You cannot physically walk faster. But now imagine someone starts stretching that rubber band. You're still walking at 1 centimeter per second relative to the rubber directly under your feet. But the rubber itself is stretching. The destination you're walking toward is moving away faster than you can walk toward it. You're obeying the speed limit. You're not walking faster than ant speed. But you're losing ground. That's what's happening to light from distant galaxies. The light is traveling toward us at exactly light speed, the cosmic speed limit. It cannot go faster. But space is expanding behind it faster than it can travel forward. For billions of years, light from the most distant galaxies was actually losing ground, moving further away from us even though it was traveling in our direction at maximum possible speed. Try to wrap your mind around that. Light, moving at 299,792 kilometers per second, the fastest thing in the universe, was moving backward relative to us. Not because it was traveling in the wrong direction, but because space itself was inflating faster than light could cross it. This is the cosmic horizon. Beyond a certain distance, currently estimated at about 16 billion light years, galaxies are receding so fast that their light will never, ever reach us. Not in a trillion years. Not in a Google years. Never. Those galaxies exist. They're real. They're out there right now. But they might as well be in a different universe. They are forever beyond our reach. Forever invisible. Forever unknowable. Think about that for a moment. There are galaxies out there, billions of them, containing trillions of stars, potentially hosting countless planets and maybe even life, that we will never see. Not because they're too faint. Not because our telescopes aren't good enough. But because the universe itself has pulled them beyond the boundary of causality. They are beyond the edge of what's physically possible for us to observe. And every second, more galaxies cross that boundary. Right now, as you read this, galaxies are slipping over the cosmic horizon, one by one, winking out of existence from our perspective. Not because they're dying, but because space itself has finally stretched enough that their light can no longer reach us. The universe is erasing itself from our view. But this is only the beginning of the impossibility. Because here's what shatters the entire picture. The universe's expansion is accelerating. That's right. It's not just expanding. It's expanding faster and faster. Every second, the rate of expansion increases. The Hubble constant isn't actually constant, it's growing. This was discovered in 1998 by 2 teams of astronomers studying distant supernovae. They expected to find that the expansion of the universe was slowing down. After all, gravity should be pulling everything back together, right? The Big Bang threw everything apart, but gravity should be acting like a brake, gradually slowing the expansion. They found the opposite. The expansion is speeding up. The discovery was so shocking, so impossible, so completely contrary to everything physics predicted that the scientists checked their calculations dozens of times. They thought they'd made a mistake. They thought their instruments were wrong. They couldn't believe what they were seeing. But the data was clear, undeniable. The universe's expansion is accelerating, and we have absolutely no idea why. To explain this impossible observation, physicists invented something called dark energy. And here's the honest truth: we don't know what dark energy is. We don't know where it comes from. We don't know how it works. We just gave the mystery a name and called it science. Dark energy is a placeholder, a confession of ignorance wrapped in scientific terminology. It's like ancient people pointing at the sky and saying, "The gods make it rain." We're pointing at the accelerating universe and saying, "Dark energy makes it accelerate." But here are the numbers, and they're absolutely terrifying. Dark energy makes up 68% of everything in the universe. More than 2/3 of reality is something we cannot see, cannot detect, and do not understand. It exerts a negative pressure, a kind of anti-gravity that pushes space apart rather than pulling it together. Dark matter, another thing we can't see or understand, makes up 27% of the universe. Everything else, all the stars, all the planets, all the galaxies, all the gas and dust, all the atoms that make up you and everything you've ever seen or touched, all the matter we can actually detect and understand. That's 5%. 5%. 95% of the universe is made of things we know nothing about. Imagine if 95% of your body was invisible, undetectable, and operated according to rules you didn't understand. That's where we are with the universe. But let's get back to this acceleration, because the implications are nightmarish. The acceleration means that over time, more and more galaxies will cross the cosmic horizon. The observable universe is actually shrinking in terms of what we can potentially see. The universe is getting bigger, but the amount of it we can observe is getting smaller. In about 150 billion years, every galaxy beyond our local group will have receded beyond the cosmic horizon. The Milky Way and Andromeda will have merged into one enormous galaxy. And from that galaxy, if any astronomers exist to look up at the night sky, they will see nothing. No other galaxies. Just stars in their own galaxy and empty space beyond. They will have no evidence that the universe extends beyond their galaxy. They will have no evidence of the Big Bang. They will have no evidence of cosmic expansion. Everything we've discovered about the universe in the past century will be impossible for them to discover. They will look at the universe and see a tiny, static island of stars in an infinite void. And they'll be completely wrong. We're lucky. We live in a cosmic moment when the universe is old enough for galaxies to form, but young enough that we can still see distant galaxies before they vanish forever. We live in the brief window when cosmology is possible. 100 billion years from now, cosmology will be impossible. Future civilizations will look at the evidence available to them and conclude they live in a small, lonely universe. They'll be missing 95% of the truth, and they'll have no way to know it. Which leads to a terrifying question: what are we missing? What evidence has already slipped beyond our cosmic horizon? What crucial pieces of the puzzle vanished billions of years ago, before Earth even formed? What's beyond the boundary we can never see? We might be like those future astronomers, thinking we can see the whole universe, while actually observing only a tiny fraction of reality. But the impossibility goes deeper still. Let's talk about what happened in the first fractions of a second after the Big Bang. Because this is where the expansion becomes truly, mind-shatteringly absurd. In the first fraction of a second after the universe began, it underwent something called cosmic inflation. For an incomprehensibly brief moment, about 10 to 32 seconds, that's 0.0000000000000000000000000000000000000001 seconds, the universe expanded faster than you can possibly imagine. How fast? The universe doubled in size, then doubled again, and again, and again, and again. About 90 times in total. In less time than it takes light to cross the distance of a single proton, the universe expanded by a factor of 10 to 26. That's 100 septillion times bigger. Let me put that in perspective. Imagine you're holding a grain of sand. It's 1 millimeter wide. Now inflate it by the same factor the universe inflated during that first moment. That grain of sand would become larger than the observable universe. Vastly larger. Incomprehensibly larger. Now inflate it by that factor again. And again. And again. Do it 90 times. That's how much the universe grew in less time than it takes light to move the width of an atom. During inflation, space expanded so fast that points in space separated faster than the speed of light. Much, much faster. Some calculations suggest speeds of 10 to 50 times faster than light. That's 100, 000, 000, 000, 000, 000, 000, 000, 000, 000, 000, 000, 000, 000, 000, 000 times light speed. It's so fast that the number becomes meaningless. Your brain cannot process it. It's not just faster than light. It's faster than light by a margin that defies comprehension. And here's what makes this so impossible to understand. This inflation solves several major problems in cosmology. The universe is remarkably uniform. Temperature, density, structure, it's essentially the same everywhere we look. But according to standard Big Bang theory, different regions of the early universe should never have had time to interact with each other. They were too far apart. Information couldn't travel between them fast enough, even at light speed. So how did they all end up at the same temperature? It's like finding out that two people who have never met, never communicated, never had any contact whatsoever, are both wearing the exact same outfit, down to the same brand of socks. Coincidence? Or something else? Inflation solves this. Before inflation, the entire observable universe was small enough that all parts were in contact. They reached thermal equilibrium. Then inflation suddenly blew everything up to enormous size. The uniformity we see isn't a coincidence. It's the result of everything starting from the same tiny region. But this creates another problem. If inflation could start, why did it stop? And if it stopped in our region of space, is it still going in other regions? The answer appears to be yes. Most models of inflation suggest it doesn't stop everywhere at once. It's like boiling water. Different bubbles of space stop inflating at different times. Our observable universe is one bubble that stopped inflating 13.8 billion years ago. But beyond our cosmic horizon, inflation might still be happening. New universes, new bubbles, might be forming constantly. This is the multiverse. Not science fiction. Not philosophy. But a direct consequence of the mathematics of cosmic inflation. If this is true, then our universe, everything we can observe, everything that will ever be observable to us, is just one tiny bubble in an eternally inflating cosmic foam. An infinite number of universes, each with potentially different laws of physics, different constants, different dimensions. Some of these universes might have stars and galaxies. Others might be completely dark. Some might last for trillions of years. Others might collapse in seconds. Some might have life. Others might be utterly sterile. And they're all expanding, all inflating, all creating more space between each other faster and faster and faster. The multiverse isn't just big. It's infinitely big. And it's getting infinitely bigger every moment. Try to wrap your mind around that. An infinity that's growing. An infinity that's becoming more infinite. Mathematically, it works. Philosophically, it's madness. But let's come back to our universe. The one we can actually observe. Because there are more impossibilities waiting. The expansion of space creates what's called cosmological redshift. As light travels through expanding space, the wavelength of that light gets stretched along with space itself. Light that started out blue might arrive red. Light that started out red might arrive in the infrared. Light that started out ultraviolet might arrive as visible light. The further light travels through expanding space, the more it gets stretched. This is why distant galaxies look redder than nearby ones. Their light has been traveling through expanding space for billions of years, getting stretched the entire journey. The most distant galaxy ever observed, as of now, is called Jade's GSZ 13-0. It's so far away that its light has been traveling for 13.4 billion years. The universe was only 400 million years old when that light was emitted. That galaxy is so young, so early in cosmic history, that it shouldn't even exist according to our models of galaxy formation. But there it is. The light from Jade's GSZ 13-0 has been redshifted by a factor of about 13.2. That means wavelengths have been stretched by more than 13 times. Ultraviolet light emitted by that galaxy arrives at Earth as infrared. We can't see it with our eyes. We need special infrared telescopes like James Webb to detect it. But here's the truly mind-bending part. That galaxy, right now, is not 13.4 billion light-years away. It's about 33 billion light-years away. Wait, what? How can light take 13.4 billion years to reach us from something that's 33 billion light-years away? That doesn't make sense. Light travels 1 light-year per year. 13.4 billion years means 13.4 billion light-years, right? Wrong. Because space itself was expanding during that entire 13.4 billion year journey. The galaxy emitted light when it was much closer to us, perhaps only 2 or 3 billion light-years away. But as that light traveled toward us, space was expanding, carrying both us and that galaxy further apart. The light had to swim upstream against the expansion of space. It's like running on a treadmill that keeps speeding up. You're running forward, but the treadmill is pulling the finish line away from you. By the time you reach where the finish line used to be, it's somewhere else entirely. So the light traveled 13.4 billion light-years through space. But space was expanding the whole time, and now that galaxy is 33 billion light-years away. Meanwhile, the light we're seeing is 13.4 billion years old, showing us what that galaxy looked like when the universe was young. The galaxy we're seeing no longer exists. At least not in that form. Over 13 billion years, it's merged with other galaxies, evolved, changed completely. We're looking at a ghost. A snapshot of something that was, preserved in light that has been traveling through expanding space for almost the entire age of the universe. But here's something even more impossible to comprehend. The current distance to that galaxy, 33 billion light-years, is increasing every second. By the time you finish reading this sentence, that galaxy will be thousands of kilometers further away. Not because it's moving through space, but because space itself is expanding between us and it. Every second, 768 kilometers of new space comes into existence between us and Jade's GSZ 13-0. Every minute, 46,000 kilometers. Every hour, 2.7 million kilometers. Every day, 66 million kilometers. In the time it takes Earth to orbit the Sun once, that galaxy recedes by 24 billion kilometers. That's 160 times the distance from Earth to the Sun. New space. Created between us and that galaxy. Every single year. And this is happening with every distant galaxy. Right now. As you read this, the universe is pulling itself apart. New space is being created everywhere, all at once, constantly. But why? What's driving this expansion? This is where we hit the wall of human understanding. Because the honest answer is, we don't know. The Big Bang Theory tells us the universe started from an incredibly hot, dense state and has been expanding ever since. But it doesn't tell us why it started expanding. It doesn't tell us what caused the Big Bang. It doesn't tell us what came before. Some physicists say there was no before. Time itself began with the Big Bang. Asking what came before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because there's no before, when time didn't exist yet. But that's a philosophical answer dressed up as physics. It doesn't satisfy the deepest question: why does anything exist at all? The expansion of space might be leftover momentum from the Big Bang. Like throwing a ball, it keeps moving because you gave it energy. The universe keeps expanding because the Big Bang gave it energy. Eventually, you might think it should slow down and stop, right? Except it's not slowing down. It's speeding up. This is where dark energy comes in. And here's what we know about dark energy: almost nothing. We know it exists because we observe its effects. We know it makes up 68% of the universe. We know it has negative pressure, pushing space apart. We know it's distributed evenly throughout space. It's not clumped like matter. We know its density stays roughly constant even as space expands, which is deeply weird because as space grows, you'd expect things to get more diluted. Imagine pouring a cup of coffee. Now imagine the cup starts growing. The coffee should get more diluted, right? More cup, same amount of coffee. But dark energy doesn't dilute. As the universe expands, the amount of dark energy seems to increase to maintain the same density. It's like your coffee cup grows, but the coffee multiplies to keep the same strength. Where does the new dark energy come from? We don't know. What is dark energy made of? We don't know. Why does it have negative pressure? We don't know. Why does it have the exact density it has? We don't know. And here's the most terrifying part: the density of dark energy appears to be fine-tuned. If it were slightly stronger, the universe would have expanded so fast that galaxies could never form. If it were slightly weaker, the universe might have collapsed back on itself billions of years ago. The value of dark energy sits in a tiny range that allows structures like galaxies, stars, planets, and life to exist. Why? We don't know. Some physicists invoke the anthropic principle. We observe the universe to have these properties because if it didn't have these properties, we wouldn't exist to observe it. It's like asking why Earth has conditions suitable for life. Well, if it didn't, we wouldn't be here asking the question. But that's not an explanation. That's an observation. It doesn't tell us why the universe has these properties. It just notes that it does. The multiverse offers a potential answer. If there are infinite universes with different properties, then by random chance, some will have conditions suitable for life. We find ourselves in one of those universes because we couldn't exist in the others. It's cosmic survivor bias. But this is untestable. By definition, we can never observe other universes. They're beyond our cosmic horizon, forever out of reach. So is this science or philosophy? Where's the line? These are the questions that keep cosmologists awake at night. But let's get back to the expansion itself. Because there's another aspect that defies intuition. Space is not expanding everywhere. You're not expanding. The atoms in your body maintain the same size. The electromagnetic forces holding your atoms together are far stronger than the expansion of space. Earth isn't expanding. The solar system isn't expanding. The Milky Way galaxy isn't expanding. Even on the scale of galaxy clusters, structures containing hundreds or thousands of galaxies, gravity is strong enough to hold things together against expansion. Space only expands in the vast voids between galaxy clusters, in the immense darkness between the great structures of the universe. It's like a foam or a sponge. The solid parts stay solid, but the holes in the sponge get bigger. The universe has structure, filaments, and walls of galaxies surrounding enormous voids. The voids are expanding. The structures are holding together. This creates a strange situation. Locally, nothing is expanding. Your body, your planet, your galaxy, all stable. But globally, the universe is expanding. The distances between galaxy clusters are growing. How do you reconcile these two facts? The answer is that space itself has no substance. It's not made of anything. When space expands, it's not stretching some elastic fabric. There is no fabric. Space is just the distance between things. And that distance is increasing. Think of it like this. Imagine two dots drawn on a deflated balloon. Draw more dots all over the balloon. Now blow up the balloon. The dots don't expand. They stay the same size. But the distances between them increase. From the perspective of any dot, all the other dots appear to be moving away. That's our universe. We're dots on an inflating balloon. The dots themselves don't expand, but the balloon's surface does. And since the balloon's surface is all we can observe, we can't see outside the balloon. It looks like everything is moving away from everything else. But here's where the analogy breaks down. The balloon is expanding into something, the three-dimensional space of the room. Our universe isn't expanding into anything. There is no outside. The universe is all there is. Space is expanding, but not into some pre-existing void. It's just expanding. Your brain rebels against this concept. It wants to ask, what's the universe expanding into? But that question has no meaning. There is no into. Space itself is expanding. That's it. It's like asking what's north of the North Pole. Once you reach the North Pole, the concept of north loses meaning. Similarly, once you reach the edge of space, if such a thing exists, the concept of beyond loses meaning. But does space have an edge? We don't know. Our observable universe has an edge, the cosmic horizon beyond which we cannot see. But that's not an edge of space itself. That's just the limit of what's observable to us. Space likely extends far beyond that. Perhaps infinitely far. If space is infinite, then it's been infinite since the Big Bang. An infinite space that's expanding is still infinite. It's not getting more infinite. Every finite region is getting bigger, but the total remains infinite. This sounds contradictory, but it's mathematically valid. Infinity is weird like that. Infinity plus 1 equals infinity. Infinity times 2 equals infinity. An expanding infinite space is still infinite at every moment. So which is it? Is the universe finite or infinite? We don't know. Current observations suggest the universe is flat or very close to flat. In a flat universe, space extends infinitely in all directions. But observations have margins of error. The universe could have a very slight curvature that we haven't detected yet. If it's positively curved, like the surface of a sphere, then space would be finite but unbounded. You could travel forever without reaching an edge, eventually returning to where you started. If it's negatively curved, like a saddle, space would be infinite but with weird geometry. Right now, our measurements say flat. But we can only measure the observable universe. What's beyond could be completely different. Maybe the universe is infinite. Maybe it's finite. Maybe it's something weirder that we don't have words for yet. The expansion continues regardless of whether we understand it. And it's accelerating regardless of whether that makes sense. Let me give you some predictions based on what we currently understand. These are the consequences of accelerating expansion. These are what the future holds if our physics is correct. In 100 billion years, every galaxy beyond our local group will have crossed the cosmic horizon. They'll be receding faster than light. Their light will never reach us. The night sky will contain only the stars of our merged Milky Way Andromeda galaxy. Everything else will be darkness. In 150 billion years, evidence of the cosmic microwave background radiation will have been redshifted into undetectability. The echo of the Big Bang will fall silent. Future astronomers will have no evidence that the universe had a beginning. In 1 trillion years, star formation will end. The universe will have expanded so much that galaxies will run out of gas to make new stars. Existing stars will burn out one by one. The universe will darken. In 100 trillion years, the last stars will die. The universe will enter the degenerate era. No more fusion, no more starlight. Only dead stellar remnants, black holes, neutron stars, white dwarfs, and brown dwarfs drifting through the expanding void. In 10 to 40 years, white dwarfs will have cooled to near absolute zero. Black dwarfs. Frozen stellar corpses in an infinitely expanding universe. In 10 to 100 years, black holes will have evaporated through Hawking radiation. The last large structures in the universe will disappear in flashes of radiation. After that, only particles will remain, scattered through unimaginably vast distances, separated by light years, then megaparsecs, then gigaparsecs. The expansion will have pulled everything so far apart that individual particles will exist in complete isolation. The universe will be dark, cold, empty, expanded beyond any meaningful structure. The temperature will approach absolute zero. Entropy will maximize. This is called heat death, the final fate of an eternally expanding universe. Not a dramatic ending, just a slow, endless expansion into cold, dark nothingness. Unless we're wrong. Unless there's something we don't understand about dark energy. What if dark energy isn't constant? What if it changes over time? Some models predict that dark energy could strengthen. If that happens, the expansion wouldn't just accelerate, it would accelerate faster and faster until it tears apart galaxies, then solar systems, then planets, then molecules, then atoms themselves. This scenario is called the Big Rip. In the Big Rip, the acceleration becomes so extreme that eventually the expansion of space overcomes every force holding matter together. First, galaxy clusters are torn apart. Then individual galaxies. Then solar systems. Then planets shatter. Then molecular bonds break. Then atomic bonds break. Then atomic nuclei are ripped apart. Finally, even the fabric of space-time itself tears. The universe doesn't just expand forever. It tears itself to shreds. Some calculations suggest this could happen in as little as 22 billion years from now. Others say longer. Some say it won't happen at all. We don't know. Because we don't understand dark energy. Alternatively, what if dark energy weakens over time? What if the acceleration slows, then stops, then reverses? In that scenario, the expansion would eventually halt. Then gravity would take over. The universe would begin contracting. Everything would fall back together. Galaxies would collide. Space would get hotter and denser. Eventually, everything would compress back into an infinitely dense point. The Big Crunch. The opposite of the Big Bang. The end of everything. But here's a wild idea. What if the Big Crunch triggers another Big Bang? What if universes bounce? Endless cycles of expansion and contraction, creation and destruction, bang and crunch, over and over forever? Some physicists love this idea. It avoids the question of, what came before the Big Bang? By saying there was a previous universe. And before that another. Eternally. But current observations don't support this. The accelerating expansion suggests we're heading for heat death or the Big Rip, not a Big Crunch. Unless we're wrong about dark energy. Which we might be. Because we don't know what it is. Here's another impossibility, the Hubble tension. Astronomers measure the expansion rate of the universe in two ways. First, they measure it locally by observing nearby supernovae and galaxies. Second, they measure it globally by studying the cosmic microwave background radiation from the early universe. These two methods should give the same answer. They don't. The local measurements give a Hubble constant of about 73 km per second per megaparsec. The global measurements give about 67 km per second per megaparsec. That might not sound like a big difference. But in physics it's huge. These measurements are precise enough that the difference is statistically significant. It's not experimental error. It's not bad data. Something is wrong. Either our understanding of the early universe is wrong, or our understanding of the local universe is wrong, or there's something fundamentally missing from our cosmological models. Some physicists think there might be new physics we haven't discovered yet. Maybe dark energy isn't constant. Maybe it varies in different regions of space. Maybe there are multiple types of dark energy. Maybe the universe isn't as uniform as we think. Or maybe we're missing something even more fundamental. What if the speed of light has changed over cosmic time? What if the laws of physics aren't truly constant? What if space itself has properties we don't understand? These are radical ideas. They challenge the foundations of modern physics. But the Hubble tension is real. Something doesn't add up. And here's what makes this truly maddening. We're living in the golden age of cosmology. We have better telescopes, better computers, better data than ever before in human history. We can see further, measure more precisely, calculate more accurately. And the more precisely we measure, the more things don't make sense. It's like zooming in on a photograph and instead of seeing more detail, you see pixels that don't fit together. The higher the resolution, the more obvious the problems become. Maybe we're on the verge of a breakthrough. Maybe some brilliant physicist will discover the missing piece and everything will click into place. Dark energy will make sense. The Hubble tension will resolve. The accelerating expansion will have an explanation. Or maybe we're completely wrong about everything. Maybe the universe isn't expanding at all. Maybe we're misinterpreting the redshift. Maybe there's another explanation for why distant galaxies look redder. Most physicists think this is unlikely. The evidence for expansion is overwhelming. It comes from multiple independent lines of observation. Redshift, cosmic microwave background, abundance of light elements, structure formation, it all fits together coherently only if the universe is expanding. But science has been wrong before. Paradigms have shifted. Theories have been overturned. Maybe it'll happen again. Or maybe the universe is just incomprehensible. Maybe we're like ants trying to understand quantum mechanics. Our brains evolved to hunt animals and gather plants on the African savanna. Did evolution equip us to understand the fundamental nature of space-time and cosmic expansion? Maybe not. Maybe we've reached the limit of human understanding. Maybe the universe is just too weird, too vast, too counterintuitive for apes with enlarged brains to fully comprehend. That's a depressing thought. But it might be true. Or maybe not. Maybe the next generation will figure it out. Maybe there's a brilliant teenager alive right now who will grow up to solve the mystery of dark energy. Maybe the equations will suddenly make sense to someone with a fresh perspective. That's the beauty of science. We don't know what we don't know. Every answer raises new questions. Every solution reveals new mysteries. The expansion of the universe is one of the greatest mysteries ever encountered by human beings. It defies common sense. It defies intuition. It challenges our understanding of space, time, and causality. Space is expanding, faster and faster, pulling the universe apart, creating distance where none existed before. And we don't know why. We have measurements. We have equations. We have models and theories and simulations. But at the deepest level, we're still groping in the dark, trying to understand something that might be fundamentally beyond our comprehension. But here's the thing. The truly miraculous thing. The thing that should fill you with wonder and awe despite all the impossibility and confusion. We can measure it. We're these tiny biological creatures on a small rocky planet orbiting an ordinary star in an unremarkable galaxy. We live for a cosmic eye blink. We're made of atoms that were forged in the cores of dying stars. We're sophisticated arrangements of chemistry that became aware of their own existence. And somehow, impossibly, we figured out that the universe is expanding. We built telescopes and satellites. We developed mathematics sophisticated enough to describe space-time itself. We made observations so precise we can measure the expansion rate of the universe to within a few percent. We discovered that 95% of the universe is made of things we can't see. We realized that space itself is expanding faster than light in some regions. We calculated that the universe began 13.8 billion years ago and will expand forever into cold darkness. We can't explain why any of this is happening. But we can measure it. We can quantify it. We can predict it. That's extraordinary. Think about what that means. The universe created conditions where matter could organize into structures complex enough to understand the universe itself. Stars formed. Planets condensed. Chemistry became biology. Biology became neurology. Neurology became consciousness. Consciousness became curiosity. And now, 13.8 billion years after the universe began, tiny collections of atoms on a minor planet are looking out at the cosmos and figuring out how it works. We don't understand everything. We might never understand everything. But we understand something. We know the universe is expanding even if we don't know why. We know space itself is being created even if we don't know how. We know we're living in a cosmos far stranger and more magnificent than our ancestors ever imagined. And we're still learning, still discovering, still pushing the boundaries of knowledge further and further. Every year brings new observations. New telescopes come online. New theories are proposed. The James Webb Space Telescope is finding galaxies so distant and so early that they challenge our models of formation. Gravitational wave detectors are giving us new ways to study the universe. Quantum computers might help us simulate cosmic evolution in ways never before possible. We're living in an age of discovery that rivals any in history. And yes, every discovery reveals how much we don't know. But that's not failure. That's the frontier. The expansion of the universe doesn't make sense. Not yet. Maybe not ever. But we're figuring it out. Piece by piece. Observation by observation. Theory by theory. We're these impossibly small creatures on an insignificant rock, floating through space at 2.1 million kilometers per hour, being carried by the expansion of space itself faster than we can measure, in a universe that's 95% invisible, accelerating toward a future we can barely imagine. And somehow, amazingly, beautifully, impossibly, we're starting to understand it. That's the real miracle. Not that the universe is expanding, but that we can know it. Not that space defies comprehension, but that we can comprehend it anyway. Not that dark energy exists, but that we can discover our own ignorance and admit it honestly. Science isn't about having all the answers. It's about asking better questions. And every mystery, every impossibility, everything that doesn't make sense is an invitation. An invitation to look closer, to think harder, to imagine bolder. The universe's expansion is impossible, terrifying, incomprehensible, and it's the most beautiful mystery we've ever encountered. You're moving through expanding space right now, being carried by forces you can't feel toward a future you can't imagine. The universe is pulling itself apart around you. Galaxies are vanishing beyond cosmic horizons. Dark energy is accelerating everything away from everything else. And you're part of it. A piece of the universe that became conscious enough to wonder about itself. A pattern of matter and energy that looked up at the stars and asked, why? The universe doesn't make sense. But we're making sense of it anyway. One impossible discovery at a time. Let's talk about what happened in those first impossible moments. Because the expansion we observe today is nothing compared to what happened at the very beginning. At 10 to 43 seconds after the Big Bang, that's 0.0000000000000000000000000001 seconds. The universe was smaller than a proton. The temperature was 10 to 32 degrees Celsius. That's a 1 followed by 32 zeros. At this temperature, the four fundamental forces of nature were unified into a single force. You need to understand how insane this is. Right now, we have four forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. They behave completely differently. Gravity pulls masses together. Electromagnetism governs light and electricity. The strong force holds atomic nuclei together. The weak force causes radioactive decay. But at that temperature, at that density, in that incomprehensibly small space, they were all the same thing. One unified force governing all interactions. Then the universe expanded and cooled. And at 10 to 36 seconds, something changed. Gravity separated from the other three forces. The symmetry broke. And this symmetry breaking released energy. Enormous amounts of energy. This energy drove cosmic inflation. The universe didn't just expand. It exploded. Not into space. Through space. Creating space as it went. During inflation, the universe doubled in size every 10 to 37 seconds. That's faster than you can conceive. Every fraction of an instant, everything doubled. Then doubled again. Then again. Then again. 90 doublings in 10 to 32 seconds. A region smaller than an atom became larger than the observable universe today. In less time than it takes light to cross a proton. Why did this happen? What triggered inflation? We think it was a quantum field called the inflaton field. As this field settled into its lowest energy state, it released energy that drove exponential expansion. But here's the problem. We've never detected the inflaton field. We don't know what particles it's made of. We don't know how it interacts with other fields. We're guessing based on mathematics that seems to work. The inflaton field is as mysterious as dark energy. Another placeholder name for something we don't understand. But inflation explains things that otherwise make no sense. Like the horizon problem I mentioned earlier. Or the flatness problem. Why is the universe so geometrically flat? Inflation stretched out any curvature until space became essentially flat, like blowing up a balloon until its surface looks flat to an ant. Inflation also explains why the universe has structure at all. Quantum fluctuations in the inflaton field, random variations at the quantum level, got stretched to cosmic scales. These tiny variations in density became the seeds for galaxy formation. Every galaxy cluster, every void, every large-scale structure in the universe traces back to quantum randomness during inflation. You're made of atoms that formed in stars. Those stars formed in galaxies. Those galaxies formed from density fluctuations. Those fluctuations came from quantum uncertainty amplified by inflation. You exist because of quantum fluctuations in the first 10 to 32 seconds of cosmic history. Your existence is a consequence of uncertainty at the smallest possible scales being inflated to the largest possible scales. Think about that. The randomness inherent in quantum mechanics, operating at scales smaller than atoms, got blown up to sizes larger than galaxies. And those random variations determined where matter would clump together, where stars would form, where planets would condense, where life could emerge. If the quantum fluctuations had been slightly different, galaxies would have formed in different locations. Different stars would exist. Earth might never have formed. You definitely wouldn't exist. Your existence depended on the exact configuration of quantum foam 13.8 billion years ago. That's not mysticism. That's physics. After inflation ended, the universe continued expanding, but at a much slower rate. It was still incredibly hot. About 10 to 27 degrees. Hot enough that particles and antiparticles were constantly being created and annihilated. Matter and antimatter in equal amounts, forming and destroying each other in a cosmic dance. At 10 to 6 seconds, 1/1,000,000th of a second, the universe had cooled enough for quarks to combine into protons and neutrons. This is called the quark epoch. Before this, it was too hot for protons to exist. The universe was a sea of free quarks and gluons. At 1 second old, the universe was about 10 billion degrees. Still hotter than the core of any star. Neutrinos decoupled from other matter at this point. Those neutrinos are still out there, forming a cosmic neutrino background similar to the cosmic microwave background but even older and harder to detect. At 3 minutes old, the universe had cooled to 1 billion degrees. Nuclear fusion began. Protons fused into helium nuclei. This process, called Big Bang nucleosynthesis, lasted about 17 minutes. In those 17 minutes, about 25% of all the hydrogen in the universe was converted into helium. Trace amounts of lithium and beryllium also formed. Then fusion stopped. The universe had expanded and cooled too much for fusion to continue. Here's what's remarkable. When we look at the oldest stars in the universe, stars that formed billions of years ago from primordial gas, we measure their composition. And we find exactly 75% hydrogen and 25% helium, with traces of lithium. Exactly what Big Bang nucleosynthesis predicts. This match between theory and observation is one of the strongest pieces of evidence for the Big Bang. We can calculate what happened in the first few minutes of the universe, and when we look at ancient stars, we see precisely the composition we predicted. But then came the Dark Ages. For 380,000 years, the universe was opaque. It was a hot, dense fog of electrons and atomic nuclei. Any light that formed was immediately absorbed and re-emitted. Photons couldn't travel far before hitting an electron. The universe was dark not because there was no light, but because light couldn't travel. It was trapped in an endless cycle of absorption and emission. Then, at 380,000 years, the temperature dropped below 3,000 degrees. Electrons combined with protons to form neutral hydrogen atoms. This is called recombination. Suddenly, photons could travel freely. Light was no longer trapped. The universe became transparent. Those photons have been traveling through space ever since, stretched by cosmic expansion from visible light to microwaves. That's the cosmic microwave background radiation, the afterglow of the Big Bang, the oldest light in the universe. When you tune an old television to a channel with no signal and see static on the screen, about 1% of that static is cosmic microwave background radiation. You're seeing the echo of the Big Bang on your TV screen. After recombination, the universe entered the cosmic dark ages. There were no stars yet, no galaxies, just hydrogen gas slowly collapsing under gravity into clumps. These clumps grew denser, hotter. After about 100 million years, the first stars ignited. Massive, brilliant stars burning hydrogen at incredible rates. These were population 3 stars, made only of hydrogen and helium, no heavier elements. They lived fast and died young. Many exploded as supernovae after just a few million years. These explosions created the first heavy elements: carbon, oxygen, iron, all the elements necessary for planets and life. These enriched clouds of gas collapsed to form new stars, second-generation stars. And those stars eventually formed the first galaxies. By about 400 million years after the Big Bang, small galaxies existed. Dim, irregular, full of hot young stars. Over billions of years, they merged and grew into the large spiral and elliptical galaxies we see today. Our Milky Way is one of those galaxies. It formed through countless mergers over billions of years. The oldest stars in the Milky Way are nearly as old as the universe itself, about 13 billion years old. Our Sun formed much later, only 4.6 billion years ago, from a cloud of gas enriched by countless previous generations of stars. The atoms in your body were forged in stars that died before the Sun was born. You're made of stardust. That's not poetry. That's fact. Every atom heavier than hydrogen in your body was created by nuclear fusion in a star, then scattered into space when that star died. The iron in your blood was created in a supernova. The calcium in your bones was made in a dying star. The oxygen you breathe was fused in stellar cores. You're a collection of atoms that have been recycled through multiple stars over billions of years. But back to expansion. For the first 7 or 8 billion years of cosmic history, gravity was winning. The expansion was slowing down. Matter was pulling back on itself through gravity, fighting against the expansion. Then, about 6 billion years ago, something changed. The universe had expanded enough that matter became spread out. Its gravitational pull weakened, and dark energy took over. The expansion began accelerating. At first, slowly. But over billions of years, the acceleration increased. Today, the acceleration is faster than it's ever been. And it's getting faster. We don't know when the acceleration started exactly. Observations suggest it was around 6 billion years ago, but there's uncertainty. What we do know is that if we look at distant supernovae from 7 billion years ago, they're dimmer than they should be. Which means they're further away than they should be. Which means the expansion has accelerated. This is what won the Nobel Prize in 2011. The discovery that the universe's expansion is accelerating. Now think about what this means for the future. Dark energy's density stays constant as space expands. But matter's density decreases as space grows. More space, same amount of matter, lower density. Over time, dark energy becomes more and more dominant. Eventually, its repulsive effect will overcome even the gravity holding galaxy clusters together. In about 150 billion years, galaxy clusters will begin to disperse. Individual galaxies will drift apart. Our local group, the Milky Way, Andromeda, and smaller galaxies, will remain gravitationally bound. But beyond that, nothing. In trillions of years, even if you had a perfect telescope that could see arbitrarily far, you'd see nothing beyond your local galactic supercluster. Everything else will have receded beyond the cosmic horizon. The observable universe will shrink. Not because the universe is shrinking, but because things are moving away so fast that their light can no longer reach us. Imagine being an astronomer in that far future. You look at the night sky and see your galaxy, some nearby galaxies, and nothing else. Infinite blackness. You measure the expansion rate, but there's nothing distant to measure. Everything nearby is gravitationally bound, so it's not expanding away from you. You might conclude the universe isn't expanding at all. You might think you live in a static, eternal cosmos. You'd be completely wrong. But you'd have no way to know it. This raises a terrifying philosophical question. What are we missing? What crucial evidence has already vanished beyond our cosmic horizon? Maybe the universe is far larger than we think. Maybe the Big Bang wasn't the beginning but just a local event in a much vaster cosmos. Maybe there are structures beyond our horizon that would completely change our understanding of everything. We can't know. By definition, we can't observe what's beyond the observable universe. But mathematics suggests there might be regions of space we'll never see. Inflation theory predicts that our observable universe is just one tiny patch in a vastly larger inflated space. Some models suggest the total universe could be 10 to 23 times larger than the observable universe. That's 100 sextillion times bigger. If you could somehow map the entire universe, our observable portion would be invisibly small, like a single atom in planet Earth. And that's a conservative estimate. Some models suggest the universe might be infinite. Truly infinite. With infinite space, infinite galaxies, infinite stars, infinite planets. If the universe is infinite, then everything that can happen will happen. Somewhere out there, infinitely far away, there's another Earth. Another you. Reading these exact words. In fact, there are infinite other Earths. Infinite other versions of you. Some identical. Some slightly different. Some dramatically different. In an infinite universe, every possible configuration of matter that doesn't violate the laws of physics exists somewhere. There's a version of Earth where dinosaurs never went extinct. A version where humans never evolved. A version where you made different choices. A version where history went completely differently. This isn't speculation. It's a mathematical consequence of infinity. In an infinite universe with finite possible arrangements of matter in any given volume, repetition is inevitable. The distance to your nearest identical copy? Probably about October 10th, 29 meters. That's a 10 followed by 10 billion followed by 29 zeros meters. Incomprehensibly far. But in an infinite universe, it exists. Does this mean anything for your life? No. You'll never meet your copies. They're forever beyond reach. Light from them will never reach you. You could never travel there even if you had infinite time and moved at light speed. But it's philosophically unsettling. In an infinite universe, you're both unique and infinitely repeated. You matter and you're irrelevant. You're one of a kind and one of infinite. Some philosophers hate this conclusion. They argue the universe must be finite. That infinity leads to absurdities. But the math doesn't care about our philosophical discomfort. If the universe is infinite, then these conclusions follow. And current observations are consistent with an infinite universe. We see no curvature in space. A flat universe extends infinitely. Unless our observations are wrong. Unless there's a curvature we haven't detected yet. Unless the universe curves back on itself on scales larger than we can measure. We're measuring the geometry of the cosmos with rulers that can only reach so far. Beyond that, we're guessing. But let's talk about something even stranger than infinity. Let's talk about quantum mechanics and the expansion of space. At quantum scales, space itself becomes uncertain. The smooth fabric of space-time we experience is an illusion. At the Planck scale, about 10 to minus 35 meters, space becomes a seething foam of quantum fluctuations. Virtual particles pop in and out of existence. Space-time itself fluctuates. Distances become uncertain. Time becomes uncertain. This is quantum gravity territory. And we don't have a complete theory of quantum gravity. General relativity describes gravity and space-time beautifully. Quantum mechanics describes the microscopic world perfectly. But they don't play well together. When you try to combine them, the equations blow up. You get infinities. Nonsense results. String theory attempts to resolve this. It suggests that particles aren't point-like but tiny vibrating strings. The different vibrations produce different particles. And at the Planck scale, space-time might have extra dimensions. Not just the 3 spatial dimensions we experience, but possibly 6 or 7 extra dimensions, curled up so small we can't detect them. If string theory is correct, then every point in space actually has these hidden dimensions. Tiny, compact, invisible to us. And the expansion of space might be affecting these hidden dimensions too. Maybe they're expanding. Maybe they're stable. Maybe they're oscillating. We don't know because we can't detect them. Loop quantum gravity offers a different approach. It suggests spacetime itself is quantized, made of discrete chunks called quanta of space. Space isn't continuous but granular at the Planck scale. If this is true, then the expansion of space isn't smooth. It's adding discrete quanta of space. Like adding pixels to a screen. More and more tiny chunks of space appearing everywhere continuously. But we can't test these theories. The Planck scale is 10 to 20 times smaller than a proton. We can't build particle accelerators that powerful. We can't probe those distances. So string theory and loop quantum gravity remain mathematical frameworks. Elegant. Potentially correct. But unproven. We're trying to understand the expansion of space without understanding what space fundamentally is. It's like trying to understand how a computer works without knowing about electricity or transistors. You can observe what it does. You can predict its behavior. But you're missing the underlying reality. Maybe space is fundamentally quantum. Maybe it emerges from something more basic. Maybe it's an illusion produced by quantum entanglement between particles. Some physicists think spacetime itself might be emergent, not fundamental. Just like temperature emerges from the motion of atoms, there's no such thing as temperature at the atomic level, just motion. Maybe spacetime emerges from something deeper. What could be deeper than spacetime itself? Information. Quantum information. The relationships between quantum states. This is speculative physics at the bleeding edge. The idea is that the universe is fundamentally made of quantum information, and spacetime is just how that information organizes itself at large scales. In this view, the expansion of space is really an expansion of information. More quantum states. More entanglement. More relationships between particles. It sounds like science fiction. But serious physicists are exploring these ideas. Because the expansion of space doesn't make sense in our current framework. Dark energy doesn't make sense. The acceleration doesn't make sense. Maybe we're asking the wrong questions. Maybe space isn't what we think it is. Here's another impossibility. The cosmological constant problem. When you calculate the vacuum energy of space using quantum field theory, the energy inherent in empty space due to quantum fluctuations, you get a number. A prediction for how much energy the vacuum should have. That number is 10 to 120 times larger than what we observe. That's not a typo. 10 to 120, a 1 followed by 120 zeros. This is the worst prediction in the history of physics. Off by 120 orders of magnitude. If the vacuum energy were actually as large as quantum theory predicts, the universe would have exploded instantly. Space would have expanded so fast that atoms couldn't form. The universe would be torn apart at the quantum level. But it's not. The vacuum energy is tiny. Almost zero. Just enough to cause the accelerating expansion we observe. Why is it so small? Why isn't it as large as quantum theory predicts? We don't know. Some mechanism must be canceling out most of the vacuum energy, reducing it from the predicted value to the observed value with incredible precision. But we don't know what mechanism. We don't know how. We don't know why. This is the cosmological constant problem, and it's been unsolved for decades. Some physicists hope that a theory of quantum gravity will solve it. Maybe when we properly combine quantum mechanics and gravity, the calculation will give the right answer. But maybe not. Maybe there's something fundamentally wrong with our approach. Or maybe it's anthropic. Maybe in most universes, the vacuum energy is huge and those universes don't last long enough for life. We find ourselves in a universe with tiny vacuum energy because we couldn't exist otherwise. That's not a satisfying answer. It doesn't explain why our universe has this property. It just notes that we couldn't observe any other value. But it might be the best answer we have. The expansion of the universe connects to quantum mechanics in ways we're only beginning to explore. The cosmic microwave background contains information about quantum fluctuations from the inflationary era. We're literally observing quantum mechanics on cosmic scales. Those tiny variations in the CMB temperature, differences of about 1 part in 100,000, came from quantum uncertainty. And those variations seeded all the structure in the universe. Every galaxy cluster formed because of quantum fluctuations amplified by inflation. The distribution of galaxies across the cosmos reflects the quantum statistics of the inflaton field in the first 10 to 32 seconds. We're seeing quantum effects on scales of billions of light years. That's philosophically profound. Quantum mechanics, which describes the microscopic world of atoms and particles, shape the large-scale structure of the entire universe. The very small and the very large are connected in ways we're only beginning to understand. And expansion is the link. Inflation took quantum fluctuations and stretched them to cosmic proportions. Ongoing expansion continues to affect quantum fields throughout space. There might even be a connection between the expansion of space and the arrow of time. Why does time flow forward? Why do we remember the past but not the future? Thermodynamics says entropy increases. Disorder grows. The universe moves from ordered states to disordered states. But why? What makes entropy increase in one time direction but not the other? Some physicists think it's connected to the expansion of space. As space expands, there's more room for entropy, more possible configurations of matter. The universe has more phase space to explore. The expansion creates the arrow of time. Past is the direction of less space, more density, lower entropy. Future is the direction of more space, less density, higher entropy. Without expansion, there might be no arrow of time. Time might be symmetric. Past and future might be indistinguishable. Your subjective experience of time flowing forward might be a consequence of cosmic expansion. That's deeply weird. The expansion of space, driven by mysterious dark energy, operating on scales of billions of light years, might be the reason you experience yesterday as different from tomorrow. The largest scales of physics shaping the smallest details of consciousness. Let's talk about what happens at the boundaries of our understanding. Because there's a place where expansion becomes so extreme that physics itself breaks down. Black hole event horizons. You know what a black hole is. Mass compressed so densely that its gravity becomes infinite at the center. Light cannot escape. Time itself stops at the event horizon from an outside observer's perspective. But here's what connects black holes to cosmic expansion. They both create horizons. Boundaries beyond which information cannot pass. A black hole has an event horizon. Cross it, and you can never return. You can never send information back out. From the outside universe's perspective, you're gone forever. The expanding universe has a cosmic horizon. Beyond it, galaxies recede faster than light. They can never send information to us. From our perspective, they're gone forever. These aren't just analogies. The mathematics is similar. Both involve horizons created by extreme space-time curvature. Both create regions of space that are causally disconnected, unable to influence each other. But here's where it gets truly bizarre. Black holes emit Hawking radiation. Stephen Hawking proved this in 1974. Quantum effects near the event horizon cause black holes to slowly evaporate. They emit particles. They lose mass. Eventually, after an incomprehensibly long time, they disappear completely. Now here's the question that keeps physicists awake at night. Does the cosmic horizon emit radiation too? Some calculations suggest yes. Empty space with a horizon, like the de Sitter space of an accelerating universe, might have a temperature. Not much. About 10 to minus 30 degrees above absolute zero. But not zero. This is called Hawking de Sitter radiation. And if it exists, it means the vacuum of space is actually warm. Infinitesimally warm, but not at absolute zero. You can't detect this temperature. It's far too small. The cosmic microwave background is about 2.7 Kelvin. This would be 10 to minus 30 Kelvin. Completely undetectable with any conceivable technology. But philosophically, it's profound. It suggests that horizons, any kind of horizon, have thermodynamic properties. They have temperature. They have entropy. The cosmic horizon has entropy. Information content. About 10 to 122 bits for the observable universe. What does that mean? What information is stored at the cosmic horizon? We don't know. But it connects to the holographic principle. The holographic principle says that all the information in a volume of space can be encoded on the boundary of that volume. Like a hologram, a 2D surface containing 3D information. Applied to the universe, this means everything in the observable universe, every particle, every field, every possible state, can be encoded on the cosmic horizon. A 2D surface containing all 3D information. You're not actually three-dimensional. You're a 2D pattern of information on the cosmic horizon that appears 3D from your perspective. Sound insane? Multiple approaches to quantum gravity lead to this conclusion. String theory suggests it. Loop quantum gravity is consistent with it. It might be a fundamental feature of reality. Space itself might be a holographic projection from a lower dimensional boundary. If this is true, then the expansion of space is really an expansion of the holographic screen. More surface area. More information storage capacity. More possible quantum states. The universe isn't expanding into three-dimensional space. It's expanding the two-dimensional surface that projects three-dimensional space. Your brain rebels against this. It contradicts direct experience. You live in 3 dimensions. You can move forward, backward, left, right, up, down. 3 dimensions are obvious. But quantum mechanics already taught us that reality isn't what it seems. Particles are waves. Observation affects outcomes. Things can be entangled across arbitrary distances. Maybe space itself is another illusion. Another emergent property of something more fundamental. The expansion we observe might be a side effect of growing holographic entropy. But let's talk about something even stranger. Something that challenges the very concept of a single universe. The many worlds interpretation of quantum mechanics. Standard quantum mechanics says particles exist in superposition. A particle can be in multiple states simultaneously until observed. Then the wave function collapses and the particle takes a definite state. But what causes the collapse? Why does observation matter? What counts as an observation? These questions have plagued quantum mechanics for a century. The many worlds interpretation offers a radical answer. Wave functions never collapse. Every quantum possibility actually happens. The universe splits into multiple branches. In one branch, the particle is here. In another branch, it's there. Both outcomes occur. Every quantum event creates new universes. Constantly. Trillions upon trillions of universes branching off every instant. You're not making choices. You're experiencing one branch while other versions of you experience other branches. If many worlds is correct, then the expanding universe we observe is just one branch of an incomprehensibly vast quantum multiverse. And every branch is expanding. Every version of the universe is growing. The expansion isn't happening in one universe. It's happening in infinite universes simultaneously. Each quantum fluctuation in the early universe didn't just create density variations. It created entire branches of reality. Every possible configuration of quantum foam during inflation actually occurred in some branch. There are universes where inflation lasted longer. Universes where it lasted less. universes where quantum fluctuations were stronger, universes where they were weaker. In some branches, galaxies formed differently. Stars are in different locations. Planets orbit different stars. Life evolved along different paths. In some branches you exist. In others you don't. In some you made different choices. In others, completely different people exist. And all of these universes are expanding. All of them accelerating. All of them heading toward heat death or the Big Rip or whatever fate awaits. The expansion of space isn't one phenomenon. It's infinite phenomena occurring across infinite branches of reality. Does this interpretation make testable predictions? Not really. Every branch is causally isolated from every other branch. You can never observe another branch. You can never communicate with other versions of yourself. So is it science or philosophy? The debate continues. But here's what's undeniable: quantum mechanics works. Its predictions are verified to incredible precision. And the measurement problem, what happens during observation, remains unsolved. Many worlds is one interpretation. Copenhagen, with its wave function collapse, is another. There are others. Pilot wave theory, consistent histories, objective collapse models. None can be definitively proven. None can be ruled out. We're stuck with interpretations of mathematics that work but don't explain why. The expansion of space might be tied to quantum mechanics in ways we don't yet understand. The measurement problem might be related to the horizon problem. The arrow of time might emerge from quantum decoherence in an expanding universe. These are active areas of research. Physicists are trying to connect quantum mechanics, general relativity, thermodynamics, and cosmology into one coherent picture. We're not there yet. But consider this. The cosmic microwave background contains about 10 to 90 photons. Each photon is a quantum particle. Each has quantum states. The universe is fundamentally quantum. When we observe the CMB, we're making quantum measurements of photons that have been traveling for 13.8 billion years. Those measurements reveal information about quantum fluctuations from the inflationary epoch. We're observing quantum mechanics on the largest possible scales, using quantum particles to study quantum events from the beginning of time. The expansion of space preserved those quantum fluctuations, stretched them, froze them, allowed us to observe them billions of years later. Without expansion, those fluctuations would have been washed out, lost to thermalization. But expansion happened so fast that different regions of space became causally disconnected before they could equilibrate. Quantum information was frozen into the structure of space itself. Every galaxy is a fossil of quantum mechanics. Every large-scale structure preserves information about quantum fields in the first instant of time. You're living inside the universe's quantum memory. Now let's talk about vacuum decay. Because there's a possibility, small but non-zero, that the vacuum of space isn't actually stable. Quantum field theory treats the vacuum as the lowest energy state. Ground state. Stable. But what if it's not the true ground state? What if it's a false vacuum? Imagine a ball sitting in a valley on a hillside. It's stable there. It won't roll uphill. But there might be a deeper valley on the other side of the hill. The true lowest point. If the ball could tunnel through the hill, quantum mechanically tunnel, not roll over, it would reach the deeper valley. The true vacuum. Our universe might be in a false vacuum. Stable for now. But not the true lowest energy state. If this is true, then somewhere, sometime, a quantum fluctuation could nucleate a bubble of true vacuum. This bubble would expand at the speed of light. Inside the bubble, the laws of physics would be different. Particles would have different masses. Forces would have different strengths. Chemistry wouldn't work. Atoms couldn't form. Stars couldn't exist. This bubble would expand forever, destroying everything in its path, converting the entire universe to true vacuum. And we'd never see it coming. It would arrive at light speed. No warning. One instant you exist. The next instant, the bubble wall passes through and you're gone. Not just dead. Unmade. The vacuum that allows your existence would cease to exist. Calculations suggest our vacuum might be metastable. Not perfectly stable, not unstable, but metastable. It could last for billions or trillions of years. Or it could decay tomorrow. The discovery of the Higgs boson in 2012 allowed more precise calculations. The Higgs field has a specific value throughout space. This value might place us in a metastable vacuum. The lifetime of our false vacuum depends on quantum tunneling probabilities. Could be 10 to 100 years. Could be 10 to 500 years. Long enough that it's not a practical concern. But the possibility exists. At any moment, somewhere in the universe, a bubble of true vacuum could nucleate. And once it starts, it cannot be stopped. The expansion of space doesn't prevent vacuum decay. If anything, it might make it more likely. More space means more opportunities for quantum fluctuations. More volume for tunneling events to occur. As the universe expands and ages, the cumulative probability of vacuum decay increases. Eventually, in the incomprehensibly distant future, vacuum decay might be inevitable. The universe destroys itself. Not through heat death. Not through the Big Rip. But through a phase transition to true vacuum that obliterates everything. This is cosmology's nightmare scenario. Not just the end of life. Not just the end of stars. But the end of the physical laws that allow anything to exist. Complete cosmic reset. Back to a lower energy vacuum where different physics applies. Would a new Big Bang follow? Would a new universe emerge with different properties? We don't know. Maybe. Maybe not. Maybe the true vacuum is completely sterile. No expansion. No structure. Nothing. The probability of this happening soon is vanishingly small. Don't lose sleep over it. But it's a reminder that even the vacuum of space, the nothingness between particles, is something. A quantum field with properties. And those properties might not be permanent. Reality itself might be temporary. Let's talk about the shape of space. Because expansion doesn't just mean getting bigger. It means the geometry of space itself is evolving. Space can curve. Einstein proved this. Mass curves space-time. Earth curves space around it, and we call that curvature gravity. But the universe as a whole has a shape. A global geometry. Current measurements say the universe is flat. Euclidean geometry applies on average. Parallel lines stay parallel. The angles of triangles sum to 180 degrees. But flat doesn't mean finite or infinite. A flat piece of paper is finite. But you could roll it into a cylinder, still flat locally, but with different global topology. Or connect opposite edges to make a torus, still flat, but finite and closed. The universe could be flat but finite. It could wrap around on itself. Travel far enough in one direction and you'd return to your starting point. This would be undetectable if the wrapping distance is larger than the observable universe. We'd never know. Or the universe could have slight positive curvature, like the surface of a sphere. In this geometry, parallel lines eventually converge. Triangles have angles summing to more than 180 degrees. Space curves back on itself. A positively curved universe would be finite, bounded but without edges. You could travel forever without reaching a boundary, eventually returning to your start. The expansion in a positively curved universe would eventually slow and reverse. The universe would reach maximum size, then contract. The big crunch. But observations show no positive curvature. Space appears flat to within measurement error. Alternatively, space could have negative curvature. Like a saddle. Parallel lines diverge. Triangle angles sum to less than 180 degrees. This is hyperbolic geometry. A negatively curved universe would be infinite. The expansion would continue forever, accelerating. Current data is consistent with flat or slightly negative curvature. Both predict eternal expansion. But here's the weird part. If the universe has a topology different from simple flat space, if it wraps around or has unusual connectivity, we might see repeating patterns in the cosmic microwave background. Imagine living on a video game screen where exiting the right edge brings you back on the left. If the universe has this topology, light from a distant galaxy might reach us from multiple directions. We'd see the same galaxy in different parts of the sky. Astronomers have looked for this. They've searched for repeating patterns in the CMB. So far, nothing. Either the universe is simply connected with no wrapping, or the topology is larger than the observable universe. We can only probe the geometry within our cosmic horizon. Beyond that, space could have any shape, any topology, any structure. The expansion we observe is local to our patch. The global structure remains unknown. Here's another impossibility. The universe's expansion should dilute matter. More space means less density. Eventually, space should be nearly empty. But quantum mechanics says the vacuum isn't empty. Virtual particles pop in and out of existence. Quantum fields fluctuate. The vacuum has structure. These vacuum fluctuations have energy, and energy gravitates. So the vacuum itself has gravity. But here's the problem. Vacuum fluctuations at small scales should dominate. High-energy virtual particles. Short wavelength quantum jitter. When you calculate the energy density of these fluctuations, you get infinity. The math diverges. Infinitely many virtual particles at infinitely high energies. Physicists use a trick called renormalization. They cut off the calculation at some maximum energy scale. Usually the Planck scale, the energy where quantum gravity becomes important. With this cutoff, the vacuum energy is finite, but enormous. About 10 to 94 grams per cubic centimeter. Observationally, the vacuum energy is about 10 to minus 26 grams per cubic centimeter. That's the cosmological constant problem again. Theory predicts huge vacuum energy. Observation shows tiny vacuum energy. The discrepancy is 120 orders of magnitude. The worst prediction in physics. Something is canceling the vacuum energy. Some mechanism reduces it from the theoretical value to the observed value with incredible precision. We don't know what mechanism. We have no theory that explains this cancellation. It's like balancing a pencil on its tip. Theoretically possible, but it requires fine-tuning to absurd precision. The slightest perturbation and it falls. The vacuum energy is balanced to 120 decimal places. Why? How? What maintains this balance? If the vacuum energy were even slightly larger, space would expand so fast that atoms couldn't form. Slightly smaller, and the universe might have collapsed immediately after the Big Bang. We exist in a universe with vacuum energy balanced to incredible precision. This is another argument for the multiverse. Maybe most universes have unbalanced vacuum energy. They expand too fast or collapse too soon. Life can't form. We find ourselves in a universe with finely tuned vacuum energy because we couldn't exist otherwise. It's not satisfying, but it might be correct. Or maybe there's new physics. Maybe quantum gravity resolves the problem. Maybe the calculation itself is wrong. We're missing something fundamental. Something about the nature of the vacuum. Something about quantum fields and curved spacetime. Something about how gravity and quantum mechanics unite. The expansion of space is intimately connected to this missing piece of physics. Dark energy, vacuum energy, cosmological constant. Different names for the same mystery. We measure it. We observe its effects. We watch the universe accelerate. But we don't understand why. And that's humbling. We've sent probes to the edge of the solar system. We've detected gravitational waves from colliding black holes. We've imaged the event horizon of a black hole. We've landed rovers on Mars. But the force driving most of the universe's energy budget? The phenomenon determining the ultimate fate of the cosmos? We're clueless. 75 years after we discovered the expanding universe, 25 years after we discovered the acceleration, we're still fundamentally ignorant about why it's happening. That should terrify and inspire you. Terrified because 95% of the universe is unknown. Dark matter. Dark energy. Our models of reality are incomplete. Inspired because we're still learning. still discovering. Every telescope reveals surprises. Every observation challenges theories. We're not done. We're not close to done. The expansion of space is the biggest mystery in cosmology. And cosmology is full of mysteries. Let me tell you about what happens to information in an expanding universe. Because this is where things become truly philosophical. Every particle has information associated with it. Position, momentum, spin, charge. Quantum states encode information. And information, according to physics, cannot be destroyed. This is a fundamental principle. Information is conserved. You can scramble it, hide it, transform it. But you cannot erase it from the universe. Black holes seem to violate this. Matter falls in. Information appears lost. Hawking radiation comes out, but it's thermal, random, containing no information about what fell in. This was the black hole information paradox. It took decades to resolve. The answer involves quantum entanglement between the radiation and the black hole interior. Information isn't destroyed. It's encoded in subtle correlations in the Hawking radiation. But the expanding universe creates a similar problem. Galaxies cross the cosmic horizon. They recede beyond the boundary where light can reach us. From our perspective, they disappear. They stop existing in any observable sense. What happens to the information they contained? Every particle in those galaxies, every quantum state, every bit of information, gone beyond the horizon. Is that information destroyed? Does it violate conservation? Or is it still there, just beyond reach? Existing but unobservable? The mathematics suggests information crossing a horizon isn't destroyed. It's encoded on the horizon itself. Just like black holes encode information on their event horizons. The cosmic horizon has entropy. About 10 to 122 bits worth. That's the information capacity of the observable universe. As galaxies cross the horizon, their information gets written onto the boundary. The holographic screen. A two-dimensional surface encoding three-dimensional information. But here's the disturbing part. The cosmic horizon is shrinking. The observable universe contains fewer and fewer galaxies over time. More cross the boundary every instant. Our information capacity is decreasing. The maximum information we can access is going down. In the far future, observers will have access to vastly less information than we do. Their observable universe will be smaller, emptier, less informative. They'll be information poor compared to us. And we're information poor compared to earlier eras. In the first billion years after the Big Bang, the cosmic horizon was smaller but matter was denser. Information density was higher. The universe's total information might be conserved. But the information available to any given observer is decreasing. You're living in an era of information abundance compared to the future. But information scarcity compared to the past. The expansion isn't just pulling galaxies apart. It's pulling information apart. Spreading it across ever larger distances. Making it harder and harder to access. Eventually, nearly all information will be encoded on horizons too far away to reach. The observable universe will contain only a tiny fraction of cosmic information. Future civilizations, if any exist, will be cosmologically impoverished. Unable to see most of reality. Unable to access most information. Limited to a tiny, isolated pocket of existence. Unless there's a way around this. Some method to extract information from beyond the horizon. Quantum entanglement might offer a loophole. If particles here are entangled with particles beyond the horizon, information might leak through. Subtle correlations that transcend spatial separation. But exploiting this would require technology we can barely imagine. And the entanglement itself would have to be set up before the particles separated beyond the horizon. You can't create new entanglement with something beyond your horizon. You can only maintain entanglement that already existed. So there might be a window. A finite time during which civilizations can establish quantum links with distant regions. Before those regions recede irretrievably. Miss that window and you're isolated forever. No communication. No information exchange. No possibility of connection. Humanity is in that window right now. For a few billion years, we could potentially establish quantum links with distant galaxies, send entangled particles, create information channels that survive the expansion. After that, it's too late. The separation is too great. The recession too fast. This is speculative. We don't have the technology. We barely understand the principles. But the physics suggests it's possible. And if we don't do it, future generations never will. The opportunity closes forever. The expansion of space creates a ticking clock. Not just for star formation or galaxy evolution, but for cosmic connection, for information exchange, for reaching beyond our local patch. Use it or lose it. Forever. Let's talk about cosmic strings. Because the expansion of space might have created topological defects, flaws in the fabric of spacetime itself. During phase transitions in the early universe, when forces separated, when symmetries broke, defects could form. Like cracks in ice. Like grain boundaries in crystals. Cosmic strings are one type. Incredibly thin. Perhaps only 10 to minus 30 meters wide. But incredibly dense. A cosmic string 1 meter long might weigh as much as Earth. These strings could stretch across the universe. Millions of light years long. Wandering through space. Expanding along with the universe. If they exist, they warp space-time dramatically. Light bends around them. Galaxies form along them preferentially. They seed structure formation. We've looked for evidence. Distinctive patterns in the cosmic microwave background. Gravitational lensing signatures. So far, nothing definitive. Either cosmic strings don't exist, or they're rarer than expected, or we haven't looked in the right way yet. But if they do exist, they're fossils of phase transitions in the first instance after the Big Bang. Preserved by expansion. Stretched to cosmic scales. Physical evidence of unification, symmetry breaking. Direct observation of the early universe's topology. The expansion didn't just stretch space. It stretched defects in space. Amplified tiny flaws into cosmic structures. Everything we observe today traces back to tiny quantum fluctuations and topological defects. Amplified by inflation. Preserved by expansion. Evolved over billions of years. The universe is a cosmic amplifier, taking microscopic phenomena and making them visible across billions of light years. Here's another mind-bending consequence of expansion. The universe has no center. People instinctively think the Big Bang happened at a point, and everything expanded outward from that point. So there must be a center. The location of the original explosion. Wrong. Completely wrong. The Big Bang didn't happen at a point in space. It happened everywhere simultaneously. Every point in space was at the Big Bang. Every location has an equal claim to being the center. Imagine the surface of a balloon again. Draw dots on it. Inflate the balloon. Every dot moves away from every other dot. But there's no center on the surface. The center of expansion is in a dimension perpendicular to the surface, the interior of the balloon. Our universe is similar, except there's no higher dimension we can access. The center of the universe, if it exists, is in a direction we cannot point to. Not up or down, not forward or backward. A direction outside our three spatial dimensions. Or maybe there's no center at all. If the universe is infinite, it never had a center. Every point is equivalent to every other point. This is called the cosmological principle. The universe is homogeneous and isotropic. The same everywhere. The same in every direction. On average. On large scales. Locally, there's structure. Galaxies, clusters, voids. But average over 1 billion light years and everywhere looks the same. The expansion preserves this. As space grows, the distribution remains uniform. More space, more galaxies, same density ratios. The universe expands uniformly because it's uniform to begin with. And it remains uniform because the expansion is uniform. It's self-consistent, but deeply non-intuitive. You're not moving away from the center of the universe. There is no center. You're stationary while space itself expands around you. Every observer sees themselves as stationary with everything else receding. And everyone is correct. It's not relative motion. It's expansion of the medium itself. Water expands when you freeze it. Ice takes up more volume than liquid water. The molecules aren't moving through space faster. The molecular bonds stretch. The medium expands. Space is expanding like freezing water. Except nothing is freezing. And there's no phase transition. Space just grows. Why does space have this property? Why can it expand? General relativity says space is dynamic. It can curve, stretch, compress. Space isn't a static stage where events occur. It's an active participant in physics. Mass curves space. Energy curves space. Pressure curves space. And curvature manifests as gravity. The expansion of space is a solution to Einstein's field equations. Given certain initial conditions, a hot dense state, uniform distribution of matter, the equations predict expansion. But the equations don't explain why those initial conditions existed. They don't explain where the Big Bang came from. They just say, given these starting conditions, here's what happens next. And what happens is expansion. Eternal expansion if dark energy dominates. Eventual contraction if matter dominates. We observe dark energy domination. So eternal expansion is our fate. Unless dark energy changes. Unless it decays or strengthens or transforms into something else. We don't know if dark energy is constant. We assume it is because observations are consistent with a cosmological constant. But we've only been observing for decades. Cosmic timescales are billions of years. Dark energy could be slowly evolving, changing on timescales longer than human civilization. We wouldn't notice yet. In a billion years, dark energy might be stronger, or weaker, or gone entirely. We're extrapolating from an infinitesimal slice of cosmic time, like observing one frame of a movie and trying to predict the entire plot. Maybe dark energy will decay. The expansion will slow. Gravity will reassert itself. Structure formation will resume. Or maybe dark energy will strengthen. Acceleration will increase. The Big Rip will approach. We're flying blind, making predictions based on minimal data, hoping our theories are correct. And that's the truth of cosmology. We observe one universe, one moment in cosmic time, one patch of space. We cannot run experiments, cannot test alternative universes, cannot rewind and replay with different parameters. We're doing science with a sample size of one. Every conclusion is tentative, every theory provisional. We're building models that fit observations. But observations are limited. There could be phenomena we haven't detected, processes operating on scales we can't observe, physics beyond our current understanding. The expansion might be more complex than we think, more nuanced, more interesting. Or it might be exactly what we think. Simple, elegant, described by the cosmological constant and nothing more. We won't know until we gather more data, build better telescopes, make more observations, develop better theories. The James Webb Space Telescope is revealing galaxies from when the universe was only a few 100 million years old. These galaxies are surprisingly massive, surprisingly structured. They formed faster than our models predicted. Does this mean our models are wrong? Or incomplete? Or just slightly off in their parameters? We're recalibrating, adjusting, learning. Every new observation refines our understanding, or reveals new mysteries. Sometimes both. JWST sees galaxies at redshift 13, meaning their light has been stretched by a factor of 13 due to expansion. The universe has grown 13 times larger since that light was emitted. These galaxies existed when the universe was only 3% of its current age. Baby galaxies in a baby universe. Except they don't look like babies. They have structure, stellar populations, massive black holes. How did they form so fast? How did black holes grow so large so quickly? Standard theories say it takes hundreds of millions of years to build large structures. But these galaxies existed before that time had elapsed. Either they formed faster than we thought possible, or our timelines are wrong, or something about the early universe was different. Maybe dark matter was distributed differently. Maybe the first stars were more massive. Maybe black holes formed through direct collapse rather than stellar evolution. Theories are being revised. Models updated. The expansion history might need adjustment. Or maybe not. Maybe these are just outliers. Statistical flukes. Rare objects that formed under unusual conditions. More observations will tell. More data will constrain theories. The truth will emerge through careful measurement and analysis. This is science at its best. Unexpected observations driving theoretical development. Reality forcing us to update our models. The universe doesn't care about our theories. It does what it does. And we struggle to understand. The expansion continues regardless of our confusion. Space grows. Galaxies recede. Dark energy accelerates everything. And we watch, measure, calculate, hypothesize, trying to understand why the universe expands, how expansion began, where it's leading. We've made incredible progress. A century ago, we didn't know other galaxies existed. We thought the Milky Way was the entire universe. Now we know there are hundreds of billions of galaxies. The universe is 13.8 billion years old. Space is expanding and accelerating. We've mapped the cosmic microwave background, detected gravitational waves, imaged black hole shadows, measured the universe's geometry. We've come so far. But the biggest questions remain unanswered. Why does the universe exist? Why these laws of physics? Why this much dark energy? These might be unanswerable. They might require information from beyond the observable universe, from before the Big Bang, from outside causality itself. Or maybe there's a breakthrough coming, some insight that makes everything click, that explains dark energy and quantum gravity and the beginning of time all at once. String theory promises this. Loop quantum gravity attempts it. Other approaches are being developed. Maybe one will succeed. Maybe in your lifetime. Maybe in your children's lifetime. Or maybe never. Maybe the universe guards its deepest secrets forever. But we keep trying. Keep observing. Keep theorizing. Because that's what humans do. We explore. We question. We seek understanding. The expansion of the universe is the greatest mystery we've encountered. And we're not giving up on solving it.